Have you ever looked at an old Java or Python program and thought, I wish this code used modern functional APIs instead? While languages like Java, Python, and C# now provide powerful functional features such as Java streams, Python's map, reduce, and list comprehensions, a huge amount of existing software is still written in the traditional imperative style. The problem is that converting imperative code into functional code is not as simple as replacing a few loops. The overall structure of the program often changes completely, making automatic translation a very challenging task. Existing rule-based tools can only handle a limited set of common coding patterns, and once the code becomes more complex, they quickly reach their limits. So, can we build a system that understands an imperative program and automatically rewrites it into an equivalent functional version? That's exactly the question this research paper tries to answer. In this video, we'll explore the paper Automated Transpilation of Imperative to Functional Code using Neural-Guided Program Synthesis. Instead of relying on handcrafted translation rules, the authors combine program synthesis, neural networks, and concolic execution to automatically generate functional code that behaves exactly like the original imperative program. The key insight behind their approach is surprisingly simple. Even though imperative and functional programs may look very different at a high level, they often share many of the same low-level expressions, and these expressions produce the same values during execution. The authors formalize these ideas as cognate grammars and trace compatibility, and use them to dramatically reduce the search space while synthesizing the target program. To make this possible, they introduce a new neural architecture called the Cognate Grammar Network, and implement the complete system in a tool named NGST2. The tool translates imperative Java programs into Java stream-based implementations and converts imperative Python programs into functional versions using functools and other Pythonic constructs, such as list comprehensions. The results are impressive. NGST2 successfully automates around 80% of these challenging imperative to functional translation tasks, and significantly outperforms existing rule-based approaches and other baseline methods. In this video, we'll break down the complete paper step by step. We'll understand the problem the authors are solving, explore the concepts of cognate grammars and trace compatibility, see how the CGN model guides program synthesis, learn how concolic execution helps prune incorrect programs, and finally look at the experimental results that demonstrate why this approach advances the state-of-the-art in imperative to functional code transpilation. So, let's get started. Now that we understand the motivation behind the paper, let's see how the proposed approach actually works through a simple example. Imagine we have a Java function called getUserRoles. This function takes a user ID and a list of insurance policies as input. Every policy contains multiple roles, such as policy owner or beneficiary, and the goal is to return all the roles associated with the given user. The imperative implementation solves this problem using two nested loops. It iterates through every policy, then through every role inside that policy, checks whether the role belongs to the given user, and if it does, adds the role's name to the output list. Now, compare that with the functional implementation. Instead of nested loops, the program first converts the list of policies into a Java stream. It then uses a sequence of higher-order operations such as flatMap, filter, and map to perform exactly the same computation in a much more declarative style. Although these two programs look completely different at first glance, the authors make an interesting observation. First, let's talk about the syntactic relationship between the two implementations. Suppose the synthesizer has already figured out the overall structure of the functional program. For example, it knows that it should use flatMap followed by filter and then map. The next challenge is deciding what expressions should be placed inside these API calls. A naive synthesizer would search through an enormous number of possible expressions. But the authors make a much smarter observation. The arguments passed to these functional operators are usually not brand new expressions. Instead, they are almost always small code fragments that already exist in the original imperative program. This dramatically reduces the search space. Existing neural-guided synthesis techniques usually predict grammar rules while constructing a program, but they don't know when to copy an existing expression directly from the source code. To solve this problem, the authors introduce a new neural architecture called the Cognate Grammar Network. CGN extends an earlier model called the Abstract Syntax Network by incorporating a pointer network. The idea is simple. Whenever the synthesizer needs to build the overall program structure, CGN predicts grammar productions just like previous models. But whenever it encounters a part of the program that is shared with the source code, it switches to pointer-based predictions and directly selects the appropriate expression from the original program. This allows the model to generate programs much more accurately while keeping the search space manageable. Next comes the second major idea, that is trace compatibility. The shared expressions in both programs not only look the same, they also produce the same intermediate values during execution. The authors use this property to eliminate incorrect partial programs before wasting time exploring them. The paper illustrates this with an example where the synthesizer constructs a partial program containing flat map and map. By analyzing the execution trace, it determines that one shared expression can only evaluate to a specific list of roles. Working forward through flat map and backward from the expected output, it concludes that map can never produce the required result, because the map operation preserves the length of the list. Since this contradiction cannot be resolved, the synthesizer confidently concludes that every completion of this partial program is incorrect and prunes it immediately. This kind of reasoning would not be possible if we only looked at the final input-output examples. So, the overall strategy of NGST2 is built on two complementary ideas. First, it exploits syntactic similarities using the cognate grammar network to guide the search toward promising programs. Second, it exploits semantic similarities through trace compatibility and concolic execution to aggressively eliminate impossible candidates. Together, these two ideas make imperative to functional code transpilation practical and highly effective. Now, let's discuss the neural guided transpilation algorithm. It combines three powerful ideas: program synthesis to generate candidate programs, neural networks to guide the search toward promising candidates, and program analysis to eliminate impossible candidates as early as possible. Let's break down the algorithm step by step. The overall procedure is called Transpile. The algorithm takes three inputs. First, it receives the source program that needs to be translated. Second, it takes a trained neural model. Finally, it receives the grammar of the target language, which defines all the valid functional programs that can be generated. The output is either a functionally equivalent target program or a failure if no valid translation can be found. The algorithm follows the well-known counterexample-guided inductive synthesis framework. However, compared to traditional CEGIS, it introduces two important improvements. First, instead of searching blindly, it uses a neural network to prioritize the most promising candidate programs. Second, instead of exploring every candidate to completion, it aggressively prunes the search space using the trace compatibility ideas we discussed earlier. Internally, the algorithm maintains two important data structures. The first is a work list, which stores all the partial programs waiting to be explored. The second data structure is a set of counterexamples. Whenever the algorithm discovers that a candidate program behaves differently from the source program, the failing input is stored as a counterexample. These counterexamples help eliminate incorrect candidates much more quickly in future iterations. Instead of expanding programs randomly, the algorithm asks the neural network a simple question. Among all the partial programs currently in the work list, which one is most likely to become the correct solution? The neural model assigns a probability to every candidate based on the source program. The partial program with the highest score is selected for further exploration. This is one of the biggest differences compared to traditional enumerative synthesis. Rather than exploring programs in a fixed order, the search is guided by learned knowledge from previously seen examples. As a result, the algorithm spends most of its effort exploring candidates that are much more likely to succeed. After selecting a candidate, the algorithm checks whether it is already complete. If there are no remaining holes, the candidate is passed to an equivalence checker. The equivalence checker determines whether the synthesized program behaves exactly like the source program. If the answer is yes, the algorithm immediately returns the synthesized program. Otherwise, the equivalence checker also provides a counterexample, an input where the two programs produce different outputs. That counterexample is added to the counterexample set, and the search continues. This is the classic CEGIS loop. Every incorrect candidate teaches the synthesizer something new about what the correct program must do. But what happens if the selected program is still incomplete? Instead of immediately expanding the partial program, the algorithm first asks another question. Is this partial program even capable of becoming the correct solution? To answer that question, it invokes a procedure called isFeasible. The algorithm examines every counterexample collected so far. For each input, it checks whether the current partial program could still satisfy trace compatibility with the source program. If even one counterexample proves that trace compatibility is impossible, the algorithm immediately rejects the candidate. Notice what this means. The synthesizer doesn't wait until a complete program has been generated. Instead, it detects impossible directions very early in the search process. The authors explain that the trace compatibility checker must satisfy two important requirements. The first is high pruning power. The checker should eliminate as many impossible partial programs as possible. The second is low computational overhead. Since this checker runs thousands of times during synthesis, each individual check must be very fast. To achieve both goals, the authors developed two versions of the trace compatibility rules. Let's look at each one. The first approach uses unidirectional reasoning based on concolic execution. If you're unfamiliar with concolic execution, you can think of it as a combination of concrete execution and symbolic execution. Known values are treated concretely, while unknown parts of the program are represented symbolically. Here's how it works. Whenever the synthesizer encounters an unknown expression that doesn't correspond to a shared term, it simply introduces a symbolic variable to represent its value. However, if the unknown corresponds to a shared expression, then the algorithm already knows all the values that expression can produce by examining the execution traces of the source program. The algorithm then propagates both the concrete values and symbolic variables through the partially constructed program. Finally, an SMT solver checks whether the symbolic result could possibly match the output of the source program. If no satisfying assignment exists, then the partial program can never become correct. The entire branch is safely removed from the search space. The paper illustrates this idea with an example involving two integer lists. The source program searches for certain numbers that satisfy a mathematical condition involving primality. Now, suppose the synthesizer proposes an incorrect functional program. Using the execution trace of the source program, the algorithm already knows the range of values that certain shared expressions can produce. When these values are propagated through the proposed functional program, the algorithm discovers that the output list can never contain the value 1, but the actual source program clearly produces the output 1. Since this contradiction cannot be resolved, the partial program is immediately discarded without exploring any further completions. Although these unidirectional rules are very precise, they have one major drawback. As the partial program grows larger, the number of symbolic expressions grows exponentially. Imagine a function with several arguments where each argument can take multiple symbolic values. The total number of combinations quickly explodes. This makes the checking procedure computationally expensive. To solve this scalability problem, the authors introduce bidirectional reasoning. Instead of reasoning only from the inputs toward the outputs, they also reason backwards from the desired output toward the inputs. The key idea is to use the inverse semantics of program operations. Suppose we already know what the final output should satisfy. Instead of allowing every possible value for each subexpression, the algorithm computes constraints on what those subexpressions are allowed to produce. If a candidate value violates those constraints, it is discarded immediately. For example, imagine we have an addition operation whose final result must always be positive. If one operand is already known to be 1, then the inverse semantics tells us that the second operand must be greater than -1. Any value smaller than that can be rejected without further exploration. By propagating these constraints backward through the program, the algorithm prevents the explosion of symbolic expressions that occurred in the unidirectional approach. Finally, the paper proves an important correctness theorem. Whenever the trace compatibility checker rejects a partial program, it guarantees that no completion of that program can ever become both trace compatible and semantically equivalent to the source program. In other words, the algorithm never accidentally removes the correct solution. Next, the paper introduces a brand new architecture called the cognate grammar network. Before understanding CGN, we first need to understand the model it builds upon. the abstract syntax network. The goal of the neural model is to learn the probability. Given a source program, what is the most likely target program? Instead of predicting the entire target program in one shot, ASN breaks this problem into many smaller decisions. Remember that every program can be represented as an abstract syntax tree. Each node in the AST corresponds to a grammar rule used while constructing the program. ASN predicts these grammar rules one node at a time. In other words, rather than assigning a probability to the entire program directly, it computes the probability of every grammar rule used to build that program. The probability of the complete program is simply the product of all those individual probabilities. To make predictions for a node, ASN also needs to know where that node is located inside the AST. For that, the paper introduces the concept of an AST path. An AST path is simply the sequence of nodes you traverse when moving from the root of the syntax tree to the current node. This path provides structural context. Next, ASN must understand the source program. To do this, the source code is converted into a sequence of tokens. Keywords such as for, if, return, operators, and identifiers all become tokens. These tokens are then processed using a bidirectional LSTM, which generates an embedding representing the source program. This embedding captures contextual information from both directions of the source code. Then another LSTM combines the source program representation with the AST path of the current node. The resulting embedding represents everything the model knows at that particular point in the generation process. Finally, a feed-forward neural network predicts a probability distribution over the grammar productions that could be used to expand that node. The model also uses an attention mechanism. Attention allows the decoder to focus on the most relevant parts of the source program when making each prediction. For example, if the synthesizer is currently generating a filtering condition, the attention mechanism may focus on the conditional expressions present in the source code. This helps the model make much more informed decisions. Although ASN works well for many program synthesis tasks, it isn't perfectly suited for this problem. Remember the key observation behind this paper. Imperative and functional programs share many low-level expressions, but ASN always predicts grammar productions. It doesn't know how to directly copy an expression from the source program. And that's exactly the capability we need. This limitation led the authors to propose the Cognate Grammar Network. CGN extends ASN with a copy mechanism, similar to the pointer networks used in text summarization. The architecture has two components. The first component is the regular ASN decoder. The second component is the copy module. For unshared non-terminals, CGN behaves exactly like ASN. It predicts grammar productions and constructs the target program normally. However, when the current node corresponds to a shared non-terminal, the model switches to the copy mechanism. Instead of predicting grammar rules, it directly predicts which expression from the source program should be copied into the target program. This is perfectly aligned with the idea of cognate grammars, where many low-level expressions are shared between the source and target languages. Of course, expressions in source code may contain multiple tokens. So the model also needs a way to represent entire expressions rather than individual tokens. To achieve this, CGN creates an embedding for each source term using the hidden states of the BILSTM. It looks at the hidden state corresponding to the start of the expression and the hidden state corresponding to the end of the expression. Using these representations, it constructs a vector that captures the meaning of the entire term. Then, during decoding, the model compares the current AST node embedding with these term embeddings. The more compatible they are, the higher the probability that the corresponding source expression should be copied. This allows CGN to intelligently decide which source expressions belong in the target program. Now let's talk about training. The model is trained using pairs of source and target programs. For every training example, the source program is given as input, and the target program acts as the ground truth. The objective is straightforward. The network tries to maximize the probability of generating the correct target program given the source program. Because every node in the target AST has a known correct action, training is fully supervised. For unshared nodes, the correct label is the grammar production that was used. For shared nodes, the correct label is the source expression that should be copied. Interestingly, the model is trained using complete programs, even though synthesis operates on partial programs during inference. This works because the network only needs two pieces of information to make predictions: the source program and the AST path to the node being expanded. Both of these are available during training. So, by examining every node in every training program, the model learns which grammar rule or which source expression it should choose in similar situations. Now let's look at how the authors actually built this system. They implemented ngst2 entirely in Python. To train the cognate grammar network, the authors used the Atom optimizer, which is one of the most commonly used optimization algorithms in deep learning. To prevent the model from overfitting, they also applied dropout, which randomly disables some neurons during training. Another technique they use is early stopping. Instead of training for a fixed number of epochs, the training process stops automatically once the validation accuracy stops improving. Finally, they apply gradient clipping, which prevents gradients from becoming excessively large and helps stabilize the training process. One major challenge the authors faced was the lack of publicly available datasets. So, they created their own. They observed that translating functional code into imperative code is actually much because every higher-order functional operator has a straightforward imperative implementation. To create the dataset, first, the authors randomly generated functional programs. Then they automatically converted each one into its equivalent imperative version. This gave them thousands of paired source and target programs that could be used to train the neural network. Once ngst2 generates a candidate program, it still needs to verify that the candidate is actually correct. For this purpose, the authors built an equivalence checker on top of Rosette, a symbolic verification framework. The verifier symbolically executes both the source program and the synthesized target program on symbolic inputs. If both programs always produce identical outputs, at least within a predefined loop unrolling bound, they are considered equivalent. Since loops are only unrolled up to a certain limit, the verification is technically bounded. This means there is a theoretical possibility that an incorrect program could pass verification. However, the authors report that they did not encounter this issue in practice. One of the strengths of ngst2 is that it isn't tied to a single programming language. The framework is parameterized by the grammars of the source and target languages. To demonstrate this flexibility, the authors instantiated ngst2 in two different settings. The first application translates imperative Java programs into Java's Stream API. The second translates imperative Python programs into functional Python using the functools library, along with constructs such as list comprehensions. The paper mainly explains the Java version, so let's briefly look at how it is configured. For Java, the authors define a small functional language that contains the higher-order operators supported by Java streams. These include familiar operations like map, filter, and fold, along with two additional operators, flatMap and find. To enable cognate grammars, the authors divide the grammar into shared and unshared components. The high-level functional operators, such as map, filter, and flatMap, are unique to the target language. These are unshared. On the other hand, variables, constants, and ordinary expressions are shared between the imperative and functional grammars. Earlier in the paper, we discussed that trace compatibility relies on forward semantics. In the implementation, the authors define symbolic semantics for every higher-order operator in the target language. For example, the semantics of map describe how every element in the input list is transformed into a corresponding output element. Similarly, filter keeps only the elements satisfying a condition. Flatmap concatenates multiple lists into one, find returns the first matching element, and fold repeatedly combines elements into a single result. These semantic definitions are converted into SMT constraints and are used during symbolic reasoning. The implementation also includes the backward semantics introduced in the previous section. Instead of only propagating information forward through the program, these inverse semantics propagate constraints backward from the desired output. Each higher-order operator has its own inverse semantics. For example, if we know the desired output of a map operation, we can infer constraints on the input list and on the mapping function itself. Likewise, the backward semantics of filter, find, flatmap, and fold determine what their inputs must satisfy in order to produce the required output. Now that we understand how NGST2 works internally, let's see how well it performs on real-world code. The authors designed their experiments around three main research questions. First, how does NGST2 compare with existing transpilation techniques? Second, how important are the different components of the system, such as the new neural architecture and the pruning mechanism? And finally, does the trace compatibility assumption limit the kinds of programs that NGST2 can handle? All experiments were run on a 2019 MacBook Pro with an 8-core Intel i9 processor, 16 gigabytes of RAM, and a timeout of 5 minutes per benchmark. Instead of evaluating only on synthetic examples, the researchers wanted realistic programs. So they built a web crawler that searched GitHub commits and Stack Overflow posts for examples where developers had manually converted imperative code into functional code. To qualify as a benchmark, each example had to satisfy three conditions. It had to contain keywords related to Java streams or Python functional programming. It had to include both the original imperative version and its functional translation. And it had to be non-trivial, meaning the imperative code contained loops, while the functional version used multiple higher-order operators. Using this approach, they collected 91 real-world benchmarks, 46 Java Stream benchmarks, and 45 Python benchmarks. The paper also provides statistics about program size. On average, Java imperative programs contain 66 AST nodes, while their functional versions averaged 40 nodes. Python imperative programs averaged 76 AST nodes, whereas the functional versions average only 38 AST nodes. So these aren't toy examples. They represent reasonably complex real-world code. Next, the authors compared NGST2 against several existing approaches. These included Segis Neo, a synthesis system based on counterexample-guided inductive synthesis; Enum ASN, which enumerates programs using the abstract syntax network; Enum sequence-to-sequence, which uses a sequence-to-sequence neural model; and for Java specifically, the NetBeans Stream Refactoring plugin, which relies on handcrafted translation rules. To ensure fairness, all neural models were trained using the same dataset and training methodology. The results were quite striking. For the Java Stream benchmarks, NGST2 successfully solved 78% of all benchmarks. The closest competing neural approach solved only 17%. For the Python benchmarks, NGST2 solved 80% of the benchmarks. The best competing approach managed only 11%. The authors explain that traditional synthesis systems struggle because they must explore an enormous search space. NGST2 dramatically reduces this search space using the trace compatibility assumption, allowing it to discard impossible candidates long before full verification. As for the NetBeans plugin, it worked well only when one of its handcrafted transformation templates exactly matched the input program. Outside those cases, it simply could not perform the translation. So overall, NGST2 substantially outperformed every baseline. The authors then investigated why NGST2 performs so well. They created several modified versions of the system by removing individual components. For example, one version removed trace compatibility pruning entirely. Another kept only the forward pruning rules but removed backward reasoning. Another ignored intermediate execution values. Others replaced the proposed cognate grammar network with the older abstract syntax network. The goal was to understand which ideas contributed the most to performance. The results clearly showed that both major innovations matter. Removing the pruning mechanism caused a significant drop in performance. Replacing the cognate grammar network with the older neural architecture also reduced performance considerably. Interestingly, depending on the benchmark, sometimes the neural architecture contributed more, while in other cases the pruning strategy was more important. But the strongest performance came from combining both innovations together. In fact, NGST2 solved more benchmarks in its first 45 seconds than any of the ablated versions solved during the entire 5-minute timeout. This demonstrates that efficient search guidance and intelligent pruning complement each other extremely well. Finally, the authors examined one important question. Does the trace compatibility assumption prevent NGST2 from handling many real-world programs? Surprisingly, the answer is no. Out of 91 benchmarks, only 3 violated the assumption. One example involved a function that searched for the first matching string, converted it to lowercase, and returned it. The functional version used a predicate that always returned true inside a find operation. The constant true did not appear anywhere in the original imperative program, so this violated trace compatibility. However, the authors observed that if the assumption is slightly relaxed to allow a few common default constants like true, false, or 0, then even these 3 benchmarks become solvable. So in practice, the trace compatibility assumption is not a major limitation for this application. Before we wrap up, let's briefly look at the limitations of this work. The first limitation is that NGST2 assumes the target language follows a specific metagrammar. While this could theoretically restrict the kinds of languages it can support, the authors found that this grammar was expressive enough to represent all the functional APIs they experimented with, including Java streams and Python's functional constructs. The second limitation is that the system requires forward and backward semantics for the target language operators. These semantics also need to be representable in a form that the reasoning engine can use. However, the authors point out that these semantics do not have to be perfectly precise. Even reasonable over-approximations are sufficient for the pruning mechanism to work effectively. Finally, the neural model requires training data. Fortunately, instead of relying on expensive, manually labeled datasets, the authors showed that automatically generated synthetic program pairs were enough to successfully train the cognate grammar network. And that brings us to the end of this paper. Although the paper focuses on imperative to functional code translation, the authors believe these ideas could be applied to many other transpilation problems wherever the trace compatibility assumption holds. Exploring those applications is an exciting direction for future research. If you'd like to dive deeper, I highly recommend reading the original research paper. You'll find the link in the description below. If you enjoyed this video and found it helpful, don't forget to like the video and subscribe to the channel. Thanks for watching, and I'll see you in the next video.